Synthux.academy. We're today hosting a workshop with Vlad Litvinenko. He's now in Berlin, I'm in Rotterdam, and we're going to be talking about classes and design a drone synthesizer. Vlad is going to take over. I'm just moderating the conversation. If you have any questions, of course, drop them in the chat. Yeah, let's get started.
All right. So, hello everyone. What are we going to do today? We are going to try to build a synth. This synth. Let me try to show it to you. Yeah. So you probably seen it already in the video that Roy prepared. So what does it have? It has these three controls, 3 pods, and one sensor, which actually works just as a button for me, just push button, and it can produce like monophonic sound, and we can control the pitch, or we can actually detune it a little bit. Because what you're hearing is actually, even when it's monophonic, it's actually 15 voices just stacked on top of each other. And also what can it do? It can produce this like evolving path, which starts with one node, then goes in some chaos, and then ends with more or less harmonic sound. And also we have a filter. Yeah, so that's the instrument, and the idea for this instrument came, like inspiration for this instrument came from Deep Note, which is a sound logo developed in 1982 for THX, and I really recommend you to go to Wikipedia, and there are also podcasts about this topic, about this sound. It's really interesting story behind creation of the sound itself, and like this machine that could handle DSP that then produced this sound. So the idea was to try to like build something like this, not quite exactly the sound that was in this logo, but something similar, and make it like this drone synth. So let's get started. We have a lot of stuff to do. Can you see now my screen with code, right? Everything is there. All right. We are starting from this simple subtractive synth example, which Roy did back in the days, and there is a tutorial video about this particular code. It's a simple monophonic synthesizer with one oscillator, one LFO, one filter, and yeah, already pretty a lot of stuff going on here. We will not go into details of this particular code, so also because it's available in previous video. So if you want to know more about this particular code, I encourage you to check this out. And what I want to show you today is how to go from this code to the synthesizer that I just shown you, that has 15 voices. And the way how to do it is using classes. At least I would highly recommend to use classes for this kind of task, because they really simplify such designs, and also they help to shapes, like when you use classes and you have this defined object, they guide you through the design. So let's just start creating them. So to add a class here, we need to go to this new tab menu, which effectively creates also a new class, and we call this class Vox and put .h. So this H stands for header. And normally C++ classes, they have two files. There is header file and also CPP file. So H file is like, it just provides information about what this class is doing, what functions are there, what it's capable of, and CPP file contains the implementation. But technically it's still pretty okay to have everything in header file, and today, for simplicity, we will stay in this single file format. So to create a class, it's actually pretty simple. We just type class, let's call it Vox. It will represent one voice of this, one of these 15 voices. And basically that's it. So we created class already. It's a completely valid class. We can already use it. The only thing that it's not pretty useful. Yeah, so we need to fill it with some functionality. So usually class has two areas: public area and private area. So everything that defined below this private word will be not visible to outside, so you cannot use it. And usually what goes here is variables, sometimes it's some internal functions, and public is actually public interface. So next, what we're gonna do is we will just look through this code and take parts that we want to encapsulate in this Vox and move them there. But before doing that, I would ask if you can hear me and see what I'm doing.
Yeah, I think it's pretty good. I think it's working pretty
well. Everything is fine. Okay, great.
Yeah, seems that I see people in the chat. I did link the original code that you're working with in the chat.
Okay.
So people can follow, and yeah, go ahead.
Okay. Great. So what do we want to put there? First, we will take this oscillator. So we will just cut it from here and drop actually in the private area. We can remove this word static. We don't need it here. In C++, usually when you create a variable, like private variable, it's like a convention among developers to add underscore to this name. So you can add underscore in the beginning. Some people do it in the beginning, some do it in the end. I do it in the beginning, at least at this point of time. And actually, because we reference this oscillator here, and oscillator itself is defined in Daisy-Duino header file that we have in main file. We should also copy this Daisy-Duino include here. So then compiler will see this oscillator definition in the header. So this is more or less like usual rule also when you define a class. Anything that you are using inside the class should be included. Let's go and see what do we have here. So we have oscillator out. It's all we don't need. Okay, then we have audio callback where everything, actually the sound is produced. We have setup where oscillator, this setup of the oscillator happens, and we have the loop where we read parameters. Yeah, so we need to replicate more or less this structure in our class. Yeah, because in our class we also will need to initialize it somehow, read and calculate frequency for the oscillator, and we will need to produce some output. So I will add here function init. It's a void, which means that it doesn't produce any output. And this name init, it's more or less convention. Yeah, so if we return to here, this is like more or less conventional. Sometimes this is init with small letters, sometimes with capital. It's more or less matter of taste. Then we will create a method called read, and this method we will use to read values from pins. And we will add another method, process. And this method has output float, because it will actually produce another sample. Okay. So then let's just copy over what we just created there. So oscillator initialization will go here. And now we see that we need, okay, I will rename it with this. Now I need sample rate here. Yeah, so something I need to add it as an input for the function, so I can then use this sample rate. And also I will use here just saw wave, not polybleep. So this is initialization so far. Then let's see what's happening with the output. So we do oscillator process, and okay, then we apply LFO. This we will do a little bit later. Now we will just say that we return oscillator process. Yeah, so and read. To read, we need actually two pins. We need to read from 2 pins. So one pin is for the names here. It's a little bit, it's old. We don't have master volume here. We have instead this is pitch, this is frequency, and this is filter. So we need these two. We need pitch to like set this pitch shift, and also the control that does this spread. Yeah, so it moves oscillator to its dedicated frequency. And what we need to take there, we need to take this oscillator frequency knob. Let's put it here so far. We will tweak it a little bit later. And we will put it here. Yeah, so we can remove it from here already. So we already moved some bits of a code over to our class. And so here we need to pass the numbers of the pins that we are going to read. So we say that we want pitch, and we want pitch pin, and we say frequency pin. And here we will use, so in DaisyDuino there is a function called fmap. What does it do? You can take the some value and map it. So we will say that we are taking the value of the frequency or pitch pin, and we divide it by 1023. Yes,
Vlad, maybe let's take a short break before it gets more advanced on this.
okay.
There's an important question from Carlo. He's asking, why do we even need classes in the first place? You might have skipped on this in the beginning, so let's take a pause and explain.
Yeah, good point. I really wanted to first show, like, to skip it to a little bit later time, but yeah, let's start from here. So when we if we look on this code, like simple code already, so it's one of the reasons. Yeah, so there are actually many reasons why we can need these classes. One reason is that it's already a lot of stuff happening here. Yeah, so we have all these initializations, we read pins, we do this, we do that. And imagine if we now like multiply it, like make it for 15 oscillators and 15 LFOs, like in this synthesizer. Yeah, we have only one filter, but oscillators and LFOs, they are like 15. So we need all these arrays, enumerate through these arrays and initialize each of it, and it will be like already a little bit hard to read through this code. Yeah, so the code becomes more and more more and more complex, I would say. Yeah, because even more stuff happening there, and if you add even more stuff, then it becomes even more complex. So the one of the functions of the classes is actually split this functionality in different in different objects in these classes, and every class has its own function, and then you compose from this predefined objects already. So you have less stuff to juggle here on the main structure of the code, yeah, in this main file. Another reasons why you want to use classes is that classes are actually, it's not only just for encapsulating codes, it's more or less like for encapsulating ideas. Yeah, so as you will see during the when we will add all this code, when we define the class for this voice, it's like we define like a character, yeah, and this character has particular like particular behavior, particular role, and then it just plays its role. You don't need to like it like lives its own life. Yeah, so you can encapsulate this behavior, and you don't have to care about all this stuff again from this top level. And when you define this class and how you define this character, there you can play a lot with how much level of control you have from outside. So what class controls itself, what you control from outside, how it communicates with outside world. So for instance, for this particular case, those classes, those voices, they will be more or less independent. So each voice lives its own life, and it just we just give it a hint where to move, and otherwise it just does what it's supposed to do. It can be the case that you want like to have more control over the behavior, but the thing is that when you design it with these blocks, it's like if you look on like on modular synthesizer, yeah, you see separate modules, and every module has its own function. Yes, it does some particular thing. So with classes, more or less you define your modules, and then you can compose them. The same as here, this synthesizer, even this simple synthesizer, is already composed from oscillator, from LFO, from filter. So each of these entities, it's actually a class behind it, which hides a lot of complexity behind and how this waveform is generated and how you control actually what's happening there when you set frequency and all this stuff. Yeah, so with this class that we define now, we go even one level higher, and then we go even level higher. And when you go on this like high level overview, in many cases it really begins to drive your decisions. It really system starts talking to you and show, okay, you have now these classes, you can combine them in some different way. And this is something that is in many cases hard to see when you just have everything in one file, which is like, I don't know, 1000 lines long. Then it's way harder to move with some different, if you want to change something and even see some possibilities how you can combine your parts of the system like in different way or rearrange it somehow. So I hope it answers. It's a little bit long answer, but I hope it answers somehow.
Yeah, thanks. I think I can summarize it. I think that the analogy of the modular system is really good here. If you have an oscillator, and an oscillator needs to, like, all oscillators will have a frequency knob, no matter what. All of them will have it. You can make one a low frequency oscillator or an audible oscillator, and these could be two instances of the same concept of an oscillator. Now we're taking it even a step further, and we're saying, what if we would take a voice? So like a subtractive voice is basically an oscillator with a filter, with a VCA, and an envelope. So if we take this and we say, this is an object now, so this is a class, then we could multiply these classes many times to create a more complex system, basically.
Yep, exactly. So it really helps manage complexity. Yeah, so let's continue. So we are here. Yeah, we are reading the pitch pin, and we say that we want to map this value to range from 0 to 500 or 500 actually, and we call it. So yeah, just a couple of words about this auto word. What does it mean? It means that the type of this pitch will be whatever this function returns. If it gives me float, it will be float. If it's integer, it will be integer. So it's like universal type that accepts whatever you throw there. Pretty convenient thing. And so to read frequency pin, we need first to define actually this how the oscillator changes its frequency. Yeah, so what you just heard, that they all start with one frequency, and then they each goes to its particular one. Yeah, so every of this voice has its own like target frequency. So and then so when we turn this the pot, then it just goes from this initial original frequency to the target one, back and forth. And the second pot just shifts this this range itself, shifts by 500 hertz. Yeah, so this frequency, when we set frequency to the oscillator, it's in hertz already. So what I want to do now, I want to define a couple of constants that will help then work with those frequencies. So one constant that I will do is actually this basic bottom frequency where we start, the bottom frequency of the range. So I can say static const. So what does it mean? Static means that it will be available on the class level. You don't need to take it. You can take it just like this, like vox, and then let me just create this frequency actually. I say k bottom frequency, and we set it to 36, which is D1 as far as I remember, but I can be wrong. But and then I can reference it like this, and I can reference it like this outside the class. I will need it later in my main file. But anyways, currently I create and const expression means that this is constant, so it will not change. You cannot change this value. It's just set as is, and you have to live with it. So then we say then we can actually read in the second pin. We can go between these ranges. I will just, yeah. So I can say auto oscillator frequency minimum. Yeah, to just give you a little bit of like heads up, we will go like this detailed only for the voice, and then we will like do a little bit fast forward to not like code everything live. But now I just want to show you the like just mechanics, how it works. Yeah, so here nothing specific will happen. Yeah, so it's not even about the class, it's mostly about just defining the behavior of this voice. Yeah, so we say we want pitch plus k bottom frequency, and we say that our top frequency is pitch plus something. So we need to tell our vox what is like target frequency, yeah, this high frequency. So what we are going to do for this, We will go into, I just cannot see it properly. We can go into the private area and say oscillator target frequency. And then we will set it when we initialize it. So we add here float oscillator target frequency. And we need to assign it. Oh, sorry, that's typo. So we say our internal one is this. And now we can use it here. Yeah, so when we will initialize those voices, we will pass to every voice, we will tell him this voice, okay, this is your target frequency, this is to, and then when we turn the knob, it's basically they are like runners, and every runner has his own target, and they will just run there. And then we can eventually we can say that oscillator frequency equal, and we will use the same fmap principle here with only so we read now frequency pin in this case, frequency pin, and we go from oscillator frequency minimum to oscillator frequency maximum. Oscillator frequency maximum. Yeah. And now we just set it. Yeah, that's it. So that's what we're doing. Returning to the topic of defining how the oscillator actually works. I mean, this how classes actually work, what they allow you to abstract, and we could even not skip this setting pins and hardcode these pins directly inside the class. Yeah, so the class can say, okay, I don't need anything, I know what my pins are, I know how to calculate frequency from them, I know everything, just initialize me and I will give you the output. But in this case, I decided to put here these pins because I want to set them from here. Because if I decide to give this code to my friend, I don't want him to like jump around the code finding where pins are, because maybe he has soldered his board somehow different. All right. So the next what we can do here is like this is the basics. Yeah, so we copy it over just the basics, and the instrument what you heard just now, it also has, every voice has also dedicated LFO which modulates the frequency of the oscillator. So with this LFO we can do basically the same. Yeah, we just take second oscillator and we drop it into box. Just a second, I need to remove. Yeah. So this is just a second. My camera actually closes the bottom of the screen. So yeah, hopefully you can see me still. Yeah. So we have LFO here, and we also can, the same way we can also put here all this initialization for the LFO here, and I'm not aiming currently for this code to be compiled right now, because I'm pretty sure that I'm doing a lot of typos. It's usually like talking and coding for me, it's like means a lot of typos. I just want to show you the principle. The code itself, the finalized code, this code is available on GitHub. So we will add the link to this code. You will have a chance to go through the final result. So and we can then also grab this. Actually, we don't have dedicated knob now for frequency. We can just remove it from here, and it's going to be here, and this frequency I will just set to something like, I don't know, something like 20. Oh, it's okay, it's initialized already, so let's leave it. So here what I can do, I can say that so what's happening actually in the instrument is when you turn this spread knob, it also applies a little bit of LFO, so it increases this LFO. So if we do it like here and we say LFO, we calculate LFO amplitude, and we do it more or less the same way. We use this fmap, and we go from 0 to really tiny amplitude, really tiny. So it's like just a little bit, to not make it a really huge vibrator. But then what does it mean? That we don't set frequency here for the oscillator. We should move it to process. So I create another variable. Oh, sorry, it's flawed. We create another oscillator frequency. Yeah, I hope I put it properly. And here I will just initialize this. Yeah, like this. Yeah, and then I say LFO amplitude, and I say LFO set amplitude, LFO amplitude. Yeah, and here we will say oscillator frequency. We will multiply by 1 plus LFO process. Yeah, so it it's going to actually multiply either by 1 or by 1005. Yeah, so really, so why I decided to multiply here instead of sorry, I have to connect my camera, otherwise it will just, yeah. So why I decided to multiply here instead of adding. So I could also add a little bit of hertz plus minus, because every frequency is different, so the amount of vibrator will be also different. Yeah, so it adds like another level of like deviations between those voices. So basically this is our voice. Yeah, so it's completely independent and more or less self-contained. The last thing is one more thing, as people say at Apple, is that how it's more or less, it's not about classes themselves, but more about these files, like when you start defining your code in multiple separate files. So when we include this vox into the main file, what does it mean for compiler, more or less? It just takes the contents of the file and just put it there. And if you include, which means that it will go through this text and see, okay, there is a class vox, so I need to define this class, I will work with it, okay, that's fine. But then imagine if you include the file twice, like we did here. So Daisy Duino included here, and Daisy Duino also included here. Yeah. What does it mean? That it will see it twice and it will try to create this class twice, which will of course lead to the compiler error. So we need to fix it, and the way to fix it is more or less, it's also like standard convention how you do it. So it's macro. We say if not defined, we call it synthux vox h. We say define synthux vox h, and then in the very end of the file we need to add and if. So what this thing is doing, you can actually, if you go into like DaisyDuino H itself, you will see that it's like everywhere in every header file you will find this construct. So it checks if this variable synthux vox is not defined, then it defines it, and of course then it goes through all the rest of the text. But if this is defined, then it will not go there. Yeah, so this file will be processed once. So for this particular example that we are doing today, it's not that important, but I just wanted to give you like a little bit of advice ahead. So if you define your classes, and especially if you do some utility classes that will be used in many places, you need to do this, otherwise compiler will complain. So we defined our box, and now we need to make 15 of them, right? Any questions so far?
Yeah, I have a couple of questions here. So first thing, Rowan asked if we can write the bodies of the methods in the header file.
Yes, we can. Technically, it again, as I mentioned, technically it works, and it considered like among like professional developers, it's still like debatable if it's okay to do it like this. But for like smaller projects, it's again for simplicity currently, for simple to just not expand too much into all these nuances of splitting between files. It's okay to have it in header file. Some functions, it's even better to do it in header file. So if you, for instance, if you want to take some value from here, for let's say you want to read the oscillator frequency. Let's say we say float oscillator frequency, and what it does, it just returns oscillator frequency, yeah, something like this, or it's only sets. So it's some really simple one-liners. Then it's in many cases recommended to add implementation to header file, because in this case those functions becomes, they by default so-called inline function. You can put it in explicitly here. So what does mean inline? Inline means it's if you use this function somewhere, instead of doing call to this function, it on compile time will actually just take a body of this function and put it on at the point where you wanted to call it. It saves the time to call function, and it's like performance optimization. Yeah. But otherwise, it's if you do really like big project and you really don't want to expose all those details, and usually you don't want to, yeah, then you split into multiple files. But for simpler projects, you can do this. It's technically okay, and it's like more or less common practice. More questions?
Sorry, just another question, or maybe a remark from Ricardo. He was saying maybe it's easier to use const instead of const expert.
Well, yeah, it can be also const. const export usually, yeah, you use when you do some more complex stuff here. Yeah, so if it's not just 36, but like something multiplied by something, so you have some function. Yeah, here we can use const also. It's fine.
Okay, and also just a reminder about the like you're actually using a lot of underscores almost everywhere. Can you repeat why is that and how we use it?
It's more or less just a convention. It's just when you write the like among C++ developers, not only C++ developers, it's in many languages, it's just a conventional thing to denote that this is private. So it goes here to private, and you mark it. So when in the code you see something with underscore, you know that this is private variable. It is something that only visible within this class. So nothing more. It's just you could invent your own convention for this, and it will be also fine. Yeah. So.
But you shouldn't.
Yeah, just
if it's private underscore. Okay.
Yeah, so just
any other questions? I'm going to collect them and ask them later on. Okay. Thanks. Let's continue.
Yeah. So then we need like 15 of those guys. Yeah. So how we do it? We do it with array, of course. So we say vox, and we call it like this, vox, and let's define also vox count 15. Yeah. And we say vox count. Yeah. So basically we have already 15 of them. So just defining it like this, it's already compiler knows that it needs to create a place for this 15 guys. And then what do we need to do? We need to, okay, this we can already remove, and we can also probably remove this. So now we need to initialize them and do something with audio callback. So when we initialize those vox, we need to go in like for loop, and usually what you will find is something like this: int e equals 0, e less than vox, k vox count, e plus plus. But I want to show you another construct which is somehow less common, people not using it too much, but it's pretty standard and pretty old. It's in C++ 11, so it's already like more than 10 years old. And this construct, this for loop, looks like this. You say auto, let's say auto, then ampersand, then we say v, or any variable. I just put v here, and vox. What does it mean? It says just take every entry is in vox, sorry, in this array. Yeah, that we defined, this vox array. So here we defined it's vox. So this is just, and now I can just say v init and pass the sample rate, and then we will need frequency. Yeah, for frequency we will talk just in a moment. So just to give you a little bit more into info about this. So this auto, again, we could just put here vox explicitly. Auto is like, more or less for me, it's already a habit to just say that, okay, whatever type of vox is, just, or this v, whatever type is there, just give me this. The most important thing here is this ampersand. So what this ampersand says, it's called reference, and it means that when I say this init, I'm doing init exactly on the guys that's sitting inside the array. If I remove this ampersand, what's going to happen? This v will contain not the guy that sits inside the array, but its copy. So it will first copy it, and then we will operate with a copy, which is not, it's just useless for us. Yeah. We want to operate exactly on our 15 voices that we have, not copies of them. Yeah, because we will not change anything there. So this is construct that you can remember. Yes, you can do it like this, but otherwise it's way more convenient than usual for loop. It doesn't require if it doesn't need to dereference everything like vox e, yeah, so you don't need all this stuff. So it's way more convenient. The only the only downside that you don't have index here. Yeah, so if you need actually index this e, then it's better to use the usual construct. And then here you can enumerate always only forward. Yeah, so it will always take from first one to the last one. Yeah, if you need to reverse it or something like this, then again you need to opt to the old stuff. And yeah, it works more or less yeah, for these arrays defined like this, or for any C++ containers, but that's already like more advanced topic. So let's look into frequency. Yeah, so we need to give this target frequency. We need to calculate somehow target frequency for every oscillator. So how was it made done in the deep node? So deep node is pretty remarkable in this sense because what they used there, and that's why this chord sounds so big. It's one of the reasons why it sounds big, because they used so-called Pythagorean, I guess I pronounce it properly, I will type it here. Pythagorean tuning. So it's in contrast to usual tuning that we use, that we see like in modern instruments. This one operates with simple ratios. So every next pitch is has ratio 3 to 2 to previous one. Yeah, so actually only two ratios used, and generally two used for this tuning to build those scales. It's 2 to 1 and 3 by 2. Yeah, and 3 by 2 is actually fifths. It's perfect fifth and a little bit bigger. This interval, this 3 by 2, is a little bit bigger than the fifths that we got used to here with equally tempered tuning. So there with this original deep node, they had their D major chord, not chord but chord, D major chord, starting from D1 and ending at F sharp 6, I guess. So it was like D1 A1, D2 A2, and so forth. Yeah, so octave and fifths, octave fifths. So it's like that's how this chord is built, and it's built from 30 voices, original one. So here we will not go into some particular chord, we will just use the same principle. Yeah, so we will take float oscillator frequency, and we take that that bottom frequency. That's why we defined it static there. Yeah, because we wanted to use it here. And now I can use here usual parentheses, and I say oscillator frequency, and I say oscillator frequency multiplied by 1.5. Yes, 3 by 2 is 1.5. And so every next frequency will be like 3 by 2, 1/5. This Pythagorean fifths higher than previous one. The only thing that I want to add here is because this frequency this way it will go pretty high. Then what I'm doing, I'm saying that if the frequency exceeds 1500 hertz, which is already around 6 octave somewhere, then I just divide it by 2. Oh, I can multiply by 0.5. Yeah, so once it exceeds this value, it will like jump 1 octave down. Then we'll calculate again 1.5 to the top, jump down. So the top of the it reaches, if I remember correctly, it reaches this 1500 at around like 10 voice already. It already reaches this, and then so the highest area of this chord will be like will contain more voices, will be in higher frequencies. So that's how we initialize it, and the same way we more or less then read those values in a loop. Yeah, so if we can use the same construct here, and we say we invox, and we say we read, what was the number? Let's see, pitch and frequency, S31, S32, S31, S32. Yeah, so that's all what we need to do here. Volume knob we don't need anymore. Okay. So LFO setup we don't need here also. So what's left is just to use it. Yeah, so here we can say we have this float output. So here we enumerate in audio callback. We enumerate through the buffers. So here, despite that this actually input and output, they are basically two-dimensional arrays. Here we have to do this usual for loop because they represented with this like pointers. Yeah, so it's not possible to use that construct here. That's why it's usually with index. So we need for every sample we also do for loop. And I say output plus equal v process, and that's it. Yeah, we don't need this, we don't need this. Yeah, so that's everything that we need to do here. About this volume, yeah, that's also important thing. When you do scaling like this, of course you need to somehow consider that when they at the same frequency and they stacked on top of each other, then it will exceed the maximum volume. So we need to. So the easiest way here is
maybe Vlad, touch on this a little bit and explain what you mean by exceeding.
Yeah. So basically, here we work with floats. Yeah, and with float, the signal, the output goes from to 1, maximum 1. Yeah, so it cannot be 1.5 or something like this. It's maximum 1. Otherwise, if on digital, if we go higher than 1, it does mean that it, let's say, if we have like 32 bits, it tries to write the, I don't know, whatever is. No, it's not about bits. Sorry, it's a wrong analogy. So it's basically tries. It tries to write to the output like the number higher than expected. And what does it mean? It that when this digital clipping appears, yeah, so you immediately it like cuts those bits that it cannot fit into this value, and then that's when you hear this like distortion and all this stuff, yeah. And so here every oscillator has maximum amplitude 1, so it will on the peak of the sine wave, let's say, or so, it will give like 1 as a value. And if we have 15 of them, 1 plus 1 plus 1 15 times, it will be 15, and we can output only 1. So what we need to do, we need to scale this down to, so basically the output should be then, the easiest way is just to divide by number of these inputs, yeah, so it will naturally do average. But there are more sophisticated ways. It can be some limiter, it can be some, or like some soft clipping solution, and if you want to drive it somehow. So, but in this case, we will just do the divide it by vox count. Yeah. So this is the easiest that we can do at this point to protect our ears. And yeah, this is also really like important, even if you do mono like we do at this point, still fill both output buffers, because sometimes it can be that you connect to some stereo, and in one channel you hear then this unprocessed buffer which can contain whatever stuff. So either set it explicitly to 0 or do like fill it with the same mono data. So that's generally it about the oscillators or these voices itself. Yeah.
There is also another question about the output and the volume. So Ricardo is asking, I didn't catch where the variable float output was initialized. It was at the top. I guess it should be 0.
Yeah, it should be 0 originally. Actually, what I'm usually doing, it's like this. So you enter callback, you set it to 0, or no, not here. So actually for every sample, yeah, right. For every sample, we initialize it with 0, then put the outputs from all our oscillators, and then we output it. So yeah, that's totally good case.
Is it important to define it as 0? I noticed that
yes.
you did it before as well.
Yes. I just in the code on GitHub, it's initialized to 0. I just forgot to do it now. So yeah, it's really important to like have some initialization always, because strictly speaking, it's not guaranteed that like this float volume here, let's say that it's 0. It just it can contain whatever. Yeah, if you define it as Boolean, it can be either true or false. It's never guaranteed. So in many cases it will be actually 0, but still it's good always to initialize value, the variable before using.
Okay, and another follow-up question. Should it ever be reset to 0 again, or it just accumulates over time?
No, here, what's happening here is like this size, it denotes how the length of the buffer. Yeah, so here we go through the buffer. Yeah, so we sample by sample we fill the buffer, and every of these samples in our case currently consist of outputs, like sum of outputs of all 15 voices. Yeah, so we do process for every sample, we go through all 15 voices, and we take output, sum it, divide by amount of voices to average it, and and then we write it to the output. So yeah, that's how it works.
So it is actually resetting every time.
Yeah. So if I do it like this, it's actually interesting. Yeah, also interesting topic. If I do it like this, what does it mean? That on first run, it will be so for e equals 0, it will fill something here. Yeah. Or then on e equal 1, it will just add on top. Then it will add on top. It will add on top. So the correct sample, only the first sample will be correct. All the rest will be already some kind of garbage. So in this case, this sum should be reset every time.
Okay, thanks.
Yeah. And yeah, so we are more or less done then with oscillators. What's left is actually filter. And for the filter, I would probably fast forward a bit, and I will just edit, just copy from existing code and go through it and explain what is there actually. So I will create a new tab. I will call it filter. And I will just copy over this code. So what do we have here? It's more or less the same what we've done for oscillator, just really smaller, but it illustrates actually this another use of classes. So I more or less intentionally did it a little bit different for filter. So in case of Vox, we actually passed in just only pins, yeah, and everything else happened inside, yeah. In case of filter, I did it a little bit different. I'm setting, so instead of exposing, so it uses under the hood, it uses the same Moog filter, Moog ladder. But instead of exposing frequency and resonance separately, I expose only one setting. I called it timbre. It can be any other name. So and here I actually set the value, so I don't put the pin here. I actually set the value of it from 0 to 1. But under the hood, it actually does this like combination of frequency and resonance, and it plays it somehow. So this is like another illustration of what class can give you. Yeah. So when you even if you wrap only one component there, like filter, what you can do with it, you can say, okay, you don't set frequency, you don't set resonance, you set this, and I will figure out something nice for you. And then you are free to change this And when you change this, the code outside has no idea about, you don't have to care about it when you work like here on the main file, or you work it on Vox. You don't need to think about how this how it's done underneath and what's happening there. Also, I can even decide at some point, okay, I don't want this implementation, this standard filter. I found some open source filter which serves me pretty well, so I just put it here, and I still expose timbre, even if this new filter has like, I don't know, 5 parameters. I still expose only one, and under the hood I decide how all these parameters will be affected by this setting. And so this way I really like a painter. Yeah, I just create my own paints. Yeah, I mix them the way how I want, and then I use this. Yeah, so it's the whole point of today's talk. I thought it looks pretty technical. What I would like to communicate, that classes, it's actually not a technical thing. Yeah, I mean it's technical, of course, but it's like something that allows you to actually sculpt to design your instrument, really design. Yeah, when you're not just fighting through these lines of code. You're not just typing something in, or you don't create this class just because it's like professional feature or something like this. But with classes, you can actually really create this like different different modules, and then connect them in different way, and then you can see immediately. So when you do this, at this point system starts talking to you. Literally, you immediately feel that, okay, for this class it's not enough not enough input, I need a little bit more control. For this class it's too much control, this class has so much control that it doesn't do anything on its own, so maybe I need to move it outside. So let's say in this example, every voice lives its own life. Yeah, so we just said, okay, just move through your frequency range, and it just moves. We could say that, okay, we don't want them to go through this chaotic state, but we want to control it all the time, that every time the relation between frequencies is something particular, so it changes, I don't know, from 3/2 to 5/4 and something like this. Yeah, in this case, of course, you need something outside that will control those classes, so you will design it a little bit different. In the end, you can take this as an instrument already and wrap it into the class and say, okay, this is my module, and then I compose with these modules. Actually, when I did my sampler, Spotify, that actually what happened. Originally, it had only one processing channel. It was just more or less standard slicer. But then once I created, like encapsulated everything in one class, it immediately was like obvious to try, okay, what's happening if I have 2, 3, 4, if they interact with each other, how all this thing works. So plugin version has 4, hardware version has 2. So, but I came to this point, to this like idea to make the multiple of them only when I had this like defined structure, and at least for me it works like this all the time, and that's what I'm trying to communicate.
I also have a note about this. When working in Ableton, many times we create a macro control and we add a bunch of different effects into one thing, like an effects chain that ends or starts with a macro control with 8 knobs. And then we would use these knobs we would assign them to multiple knobs in the effect chain. So then we have a MIDI controller controlling one knob, but it is actually controlling a bunch of them. And this is where we actually become designers. We're designing the way that the instrument will behave. So with C++ here, this becomes more granular. You can really define how the knob is going to behave. We had a conversation on Discord with Chris, who is designing the Wiggler instrument, which is fantastic. If you don't know about this instrument, you should really check it out. It's not really out there yet, but he's like really showing all his process, which I love. The question was about the volume knob, and should it be bigger or larger? And then we dove into like what is the functionality of the knob in a guitar or in a synthesizer. And then we suggested that maybe it would be interesting to add some distortion on this knob. So like saturation. So when you just use the knob regularly, let's say up to the half point, you would get regular volume. But the further you go beyond the half point, you're going to add some saturation, which is going to make the instrument feel more natural, which in this particular instrument, I think makes a lot of sense. So it's all these little details that conceptually make sense in your head, and then you're not really sure how to do them. And what Vlad is now explaining here, I think, is really tapping right into this. Like, how do you actually make a knob do multiple things? You actually think in classes and you combine things together, and yeah, makes it easier to work with.
Yeah, this is definitely a really big topic as how you can modify behavior of controls with classes if you define really like class for it. Like for instance, I have here, I don't know if you can see it. Let me just check. Yeah, so I have this touch sensor. So it works only when I touch it. But if I want to make it a switch, the class is actually way to go. I just define a class, one state variable. When I touch once, it sets to true. Touch second time, I move it back to false, and I suddenly have a switch. Yeah, so, and the code around it doesn't even know what is the hardware thing behind it. Yeah, it just knows that, okay, this thing can be on or off. And you can have actually opposite thing for the switch. You can say that, okay, this thing triggers some event only when something is changed. So you can turn the switch into push knob. Yeah, you switch in one direction, another, but actually it just triggers some event. And with knob is just a universe of possibilities what you can do with just one simple pod, using class and redefining the behavior of it. All right, so yeah, probably that's mainly what I wanted to show now. Again, this is not this code is not quite polished. We would need another like hour to like polish everything. And yeah, the code itself is on GitHub. You can just go there, just check it out. And yeah, that's probably that's it from my side. So if you have more questions, let's jump.
Yeah, maybe switch to the other view. And if you guys have any questions, feel free to ask in the chat, and I'll bring them up.
Okay, just a second. I need to. Okay.
This was great, Vlad. I learned a lot of stuff.
I hope so.
We did share the code. If you just scroll a bit up in the chat, you'll see there's a link directly to the code.
Yeah.
If you guys are new to synthux.academy, we're on Discord. That's where we basically learn most of the stuff. If we work on projects together, or we ask questions about technical things, about design, about code, it's a really good place to be. Yeah, thank you so much for joining us. Vlad, thank you so much for taking the time for this.
Thank you.
And uh, is there any picture of the board? What do you mean exactly? The board that he's using, that's
It's yeah. Oh, yeah. Can I? Yeah.
you can actually see it on the website. If you go to Synth Academy, on the homepage, there are
Oh, sorry.
actually, yeah, actually, if you go to the shop, that's easier maybe to see it, the
Yeah.
small one.
It's a simple fixed board. It's my favorite one.
Um,
It's really great, actually, as a for this kind of prototyping, because it has like this limited number of controls, and that's why it gets really interesting. And it's again comes to defining behavior of those pods. So
yeah,
yeah,
actually, when we worked on the Spotikach looper, like I told Vlad, okay, we have to work with no multiplexer, so we can use only 12 knobs. I was like, we narrowed it down from 4 loopers to 2 loopers, and now we need to have like even a smaller
yeah,
version.
yeah.
Um,
Originally it was 19 knobs. Yeah,
yeah. Um, but I feel like every time that we take these, like we have these constraints, we actually make something that's a bit more refined, because you really need to make, you need to make design decisions on how to make things work. Yeah, I see some more notes. When developing new C++ code and libraries, how do you go about testing your work to ensure it's working as expected? Verify upload or obvious, but I was wondering if you had any pro tips.
this is actually big topic, really big, and I would say it's my favorite topic, and it has actually it's a lot to do with architecture, with classes, with architecture, with all this stuff. So um, I don't know, probably currently it will be a little bit hard to share my screen with the Spotikach code. It has really a lot of different classes, different stuff, and the key what to all this stuff is to make your to really understand this border between the functionality of the instrument and the system environment around it. Yeah, so if you do, for instance, uh, like when you are working with Daisy Duino, yeah, and you define, in my case it was sampler, yeah, so I tried to define my classes the way they don't know about Daisy Duino at all. There is no mention of the, in my case it's libdaisy, but doesn't matter, yeah, so it doesn't know about the environment where it runs. It just has it's only, so it uses just some common types, common constructs. And if you do it like this, really, then you can take your class, your object, and you can like say, okay, then you do what software developers call unit testing. You put there some input and you know what should be output. Yeah, even if you do DSP, there is also this like testing that when you send like different frequencies, one impulse, yeah, so it's also like some set, so it's not only just for plain functionality. And even if you have like something more complex than one class, let's say your one class depends on many different classes, then it goes even more further. You can, in C++ you have so-called abstract classes. So to abstract class, it has no implementation. It only defines the interface. Yeah, so this is a function, like let's say this is a function process, and that's it. And then you can have multiple implementation, and you can use any of this implementation instead of this abstract one. It's again, it's more like it's more advanced topic already. But my pro tip for this would be try to define classes uh, again, not for the sake of defining classes, but for trying to put this border between your code, your implementation, your functionality, and the environment around it. And usually it's really easy to track. Once you see that you need to include DaisyDuino in your class, it means that, okay, it already depends, you need to upload it. Yeah, if you use oscillator or something like this there, if it uses something from this library, maybe you can. I never tried to run this like in some emulator somehow on desktop. So usually what I'm doing, I'm trying to abstract as much as possible from the environment, and then I can test it. So
okay. We have also a question about the audio callback from Rowan. We didn't cover this now because it's a bit. We actually covered it in a complete video course. So if you go to the synthux.academy website /simple, you can see the complete platform, and at the bottom of it there is actually a link to a hidden link to a complete course. There is a really clear explanation with some examples of how exactly it's working. So I think that's the best way to do that. Ryan asks, why don't you want a multiplexer? It was just a challenge because we wanted to present the platform, the simple platform, at Superbooth, and we had a really simple project from Nick Donaldson from Infrasonic Audio, which actually in the back side of it is super complex, only C++, and like he really writes his own DSP, and it's just absolutely remarkable. But in terms of the interface, it's like the easiest to build. And then we had Spotikach from Vlad, which was like in between, no multiplexer, but with a touch sensor. So it's like an in-between build. And then we had from Lucas Bonvin, the more advanced version of the board, which is basically an additive synthesis, a synthesizer inspired by the Buchla music easel. And we had a funny story there. We actually called it micro easel, and then the owner of Buchla came to visit us on Superbooth and was like, I don't think you should use this name like this. And we became friends, and it was nice because he was like super nice. He was like, yeah, we might use this name at a certain point, so you need to come up with something else. And then we figured we'll call it Music Canvas instead. But it's literally a copy, just a smaller version of it as a design challenge. Yeah, so that's the reason why we didn't use a multiplexer. Okay, so another question with Carlo. I actually didn't get why in the audio callback we reset the output every loop and then add it to the process instead of simply make it equal process.
Because just a second, let me return here. Because we have 15 of these processes. So if it's one oscillator, if it's just one oscillator, then yeah, that's how it was originally. Yeah. So if you look into original code of the simple synthesizers, then yeah, output is just oscillator process, and that's it. But here, what do we need? We need to go and accumulate the output from all 15 voices for every sample. That's why we need this like step to do this. Just because there are 15 of them now.
Okay. Is there a C++ unit testing framework that works with Arduino, DaisyDuino?
I don't know. So far, yeah, as I mentioned, I didn't try to use to run actually DaisyDuino with all the library inside some code. I don't think it will work because it relies on hardware abstraction layer and all this stuff. So I don't know if there are actually emulations, software emulations of the MCU. So what I'm using like pretty standard C++ frameworks, but again, it works because what I'm testing usually it's independent from the environment. Yeah, so like for Spotty Catch, for instance, I was testing my trigger, how that it properly goes through through all the steps and sequencer works properly. So all this code is pretty independent, so there I can use whatever is available. But for specifically for Daisy Duino, so far I haven't seen.
Great, thanks. Yeah, I see that questions are done. So thanks again, Vlad, for joining us and explaining so much.
Thanks for
Thank
having
you.
me.
Yeah, definitely. Thank you, everyone, for joining us. Please like and subscribe to beat the YouTube algorithm or inform it that this was valuable for you, so other people, like-minded people, could see it as well. And if you have any questions or you have any suggestions for content that you would like us to work on, please do share. We are on Discord, on Instagram, on YouTube. Synth.academy is basically a nonprofit that I'm running from my house in Rotterdam, and it's super nice to see so many people joining and collaborating and working on projects. Yeah, feel free to suggest anything, and we're going to we're going to try to make it work. Thanks for joining.
Thank you.
Right.